Chapter 12 is statics and material properties, something to that effect. Most of you will take an entire class dedicated to engineering statics. Most of you will take another class dedicated to engineering materials. So what you very well might take two entire classes on, we're going to accomplish via a relatively short chapter 12. And it's a good heads up. And this is very consistent with what we've been with what we've been doing thus far in terms of the force analysis method. So I'm just double checking some stuff here, and I'm going to check the date, the availability. Okay. All right. I think if you refresh now, you should see chapter 12, quiz 1 in Wiley Plus, and it should be this homework problem that you see here. And this is welcome to the world of equilibrium. So let me give you the 25-cent tour of the $100 YouTube green sheet lecture video. This is equilibrium. And there's equilibrium, and then there's static equilibrium. Here's what equilibrium means. Equilibrium means the following. There's no rotational acceleration. There's no linear or tangential. Those are equivalent terms. Linear acceleration, tangential acceleration, translational acceleration, those all mean the same thing. So there are no accelerations in equilibrium. Here's static equilibrium. It means the same thing. No rotational acceleration, no linear acceleration, no velocity. So this is force analysis for objects that are at rest. And there's, I think, obvious need to do this. If you design a part or an assembly or a device, you need to know the underlying forces that that part needs to withstand or needs to produce. So I'm actually trying to think of examples where you don't care about this, and I'm not really coming up with anything. Any type of device that I can think of is going to come along with the need to know what the forces, the underlying forces are in terms of the forces that need to be dealt with or produced. So, I mean, the classic example would be a bridge. If you design a bridge, you have to know the forces that are the forces that are acting on a bridge, so you can design appropriately. So you can design so that those forces don't cause any type of problems, material failure or deformation or anything like that. So there's lots of reasons. And typically what you do is you study a situation, you say, okay, here are the forces, and then you take that information, you go into like a finite element analysis, or you go into computational fluid flow or a dynamic response analysis. You say, okay, well, now that I know my forces, I got to figure out, should I make this out of stainless steel or should I use some sort of polymer, depending on this. So on it, the examples boggle the mind. Here you have a bicycle wheel. You have a bicycle wheel, and you're applying this force, or there is that horizontal force applied to this bicycle wheel, and this bicycle wheel is raised up to that higher level. So it's like you're running into a curb, and you apply a force, so this bicycle wheel just has enough oomph to go like that. And the bicycle wheel will literally climb up or attain this higher level. We'll make it to the higher level going up the curb. So here would be here to be this wheel that's made. Aha, good, I made it. So the whole purpose of this force is to get the wheel up to that higher level, get up above the curb. All right, so that's what we're doing. And in so many ways, there's nothing new in this chapter. Really, there is almost nothing new. In some ways, this is just like reinforcement. This is reinforcing. It's reinforcing force analysis, and all of this falls under the domain of force analysis method. In fact, if you look up the force analysis method in your green sheets, it actually does include, stuff for X force inventory, Y force inventory, and torque inventory. So there's no adjustments that need to be made to the force analysis method that's in there. So here we go. Let's figure out what that minimum force is. My first thing, just thinking of force analysis method, I'm thinking of free body diagram. So I'm going to just stick with the tried and true practices. Here's my force vector. I'm just going to overlay that. That's my force vector. That's my external force. And this might come from whatever. This is probably pedals. Like this is a resultant force that derives from the pedals and the sprocket and the gearing of your bicycle. But you have this force acting on the axle of that bicycle wheel. That's a force. Here's another force. Another force would look like this, the weight force. And the weight force acts on the center of mass. And that's the center of mass. And we've mentioning now a lot this term center of mass. Center of mass is the point at which all of the objects and material can be considered to be located. So it's like a surrogate or a stand-in or a proxy for all of the objects' mass, all at one single little point. All right, so there's the weight force mg. There's a normal force. I guess I better switch colors. Actually, there's two normal forces. Here's one of the normal forces. There. That is a normal force, which means it's a Newton's third law reaction force. Here's another normal force. I guess I'm using multiple colors. Another normal force is right here. A little bit too thick. Right here. Okay. Let me just tweak this. So, I guess that's it. I think that's it. So let me label it. This is a normal force. I'll call it just normal force number one. And remember what a normal force is. A normal force is a reaction force that's perpendicular to a shared contact surface. So this would be this gray line that I'm drawing right here. This would be the shared contact surface between the tire, the wheel, between the wheel and the curb right here, right at that point as indicated. Okay, so I have one normal force. I have another normal force. This would be Fn2, I suppose, Fn2. There's mg, and then here's my external force, F, right here. And I'm just not thinking about anything other than my free body diagram, and I don't think I'm missing anything else. So my free body diagram looks good. So it's business as usual, free body diagram. I have to worry about coordinate systems. And so there's nothing interesting or there's nothing weird to do with my rectangular coordinate system or my orthogonal coordinate systems. This, let's just say that's X, that's Y. I have to worry about my rotational coordinate system. And this is me doing that. My rotational coordinate system looks like this. I'm just going to stick with the default. The default says anything going counterclockwise is positive. So positive is as indicated. This is positive. This is my AOR right here, my axis of rotation, right there. Axis of rotation. Well, and then here's the question. I mean, is it? And here's my rule of thumb. If there's a physical point that is clearly the axis of rotation, use it as your axis of rotation. Now, having said that, technically speaking, I could pick any point of the axis of rotation. And then the question is, well, that's true. You could. I mean, so that sort of takes the pressure off. I could select any point of the axis of rotation, and you're going to get the right answer. The question is, maybe there's an easier versus a harder path based on your axis of rotation. So, but again, the good news is, you know, pick any point. I'm picking this point because sort of my rule of thumb is, if you can see the physical axis of rotation, go ahead and select that as your analytical axis of rotation. And when I actually write this coordinate system, I need to make it clear that this rotational coordinate system is pertaining to that axis of rotation right here. So this is plus. All right. All right, there's the forces. So everything's set up, ready to go. I guess it's time for torque analysis. I'll start with torque analysis. Number one, let's do torque inventory. Torque inventory, which says the sum of all torques equals I alpha. This is Newton's second law, just like we had in the good old days. F equals ma. Now we have sum of all torques equals I alpha. So I'm just going to add up all of the torques, and I might have, let's see, and this is where I'm not thinking too deeply now. I'm just tallying up everything. I could have a torque due to mg. That's a force. So if it's a force, maybe it produces a torque. I might have a torque due to Fn1. I might have a torque due to Fn2. I might have a torque due to F. So is that it? I have Fn2, Fn1, mg, F. I've accounted for all my forces. Now I just have to worry about plus or minus. mg is producing a positive torque. And this is where I'm using pop can right-hand tool. Remember this? I think I ran through this. This is the official right-hand shape. You have to grab a container of great value disinfecting wipes, and you have to extend your thumb like this. And then this is right-hand rule number 2. It's like you're holding a cup with your thumb extended. So right-hand rule, this is your right-hand rule shape. It's technically right-hand rule number 2, or I refer to this as pop can right-hand rule. It's like you grab a can of pop and you extend your thumb and you freeze your hand in place. So this is how this is how I determine the plus or minus sign on torque. Your fingers curl in the direction of the force and your thumb points along the AOR. So if I'm looking at mg, I'll play this with mg. Here's mg. So my fingers are going to be curling in the direction of mg. This is the direction of mg. Mg, I have to curl my fingers so they flow in the direction of mg, and then my thumb points in the direction of the AOR, of the plus or minus. My thumb is aligned with the AOR, and it points in the direction of the torque. So if I'm doing this, if I'm using the officially sanctioned physics right-hand rule shape, my fingers, I'm curling in the same direction as that mg force. Look at this great demonstration I'm doing. My thumb is aligned with the AOR, and the direction my thumb is pointing, that tells me the plus or minus. So according to this is coming out of the screen or in the positive Z direction, or what I'm calling positive. So this gets a positive sign. We should talk about that a lot, because the only reason I'm spending a lot of time talking about this point is it's a tripping point. It's a tripping point. It's not uncommon for students just to not get what I'm saying, because maybe I'm not explaining it clearly enough, or maybe it just needs a lot more attention. But the bottom line here is that right-hand rule approach is pretty darn helpful. The other way, if you didn't like that, let's just say you don't like that method, or if you're like me, you want an alternative method. Here's the alternative method. Torque is equal to R cross F. So basically what you do here, it's still kind of a right-hand rule, but this means you're going to cross R into F, R into F. We dealt with this. I think we did this last time. Let me just ask you guys this question. Did we go through the unit vector multiplications? Did we do this was
unit? We did that.
So we did all that. So that's good. Yeah. Did we? Well, stop me. And I won't repeat it then, but this is I hat. This is J hat. This is K hat. So I remember, I think I threw out some questions. This is actually worth a bit of a review. I basically said, what is I cross J? What is I cross K? What is J cross I? What is J cross K? And then what is K cross I and K cross J? And then we could go on. I could actually repeat 6 more, and well, more than that. All right, so let's just go through. Is everyone agreeing that I cross J is equal to K? And that's right-hand rule number 2. I'm assuming the officially sanctioned physics right-hand rule shape, and I'm going to stick to the rules here. I am going to curl I into J. So my fingers are curling in that purple arrow direction. And if I'm curling I into J, my thumb points in the direction of the result. My thumb points in positive K. So that's how I use right-hand rule to get I cross J spitting out K hat. All right, so I cross K, same thing. I have to cross or curl or swing or rotate. I have to rotate vector I hat into J hat, because it's I cross J, not J cross I. So K stays home, and I get swung into K. And my right-hand rule, I don't have any choice here. This is showing negative K. So you might have learned this through a mnemonic, just sort of like a rote memorization scheme or like a memory trick, which is fine. But knowing how to do this with the right-hand rule will pay dividends. J cross I have to curl J into I, that's minus K. J cross K is equal to I hat. K cross I is J hat. And K cross J is minus I hat. So I think we did this before, but it's good to go through it again. In this case, if it's R cross F, let's just make a little substitution here. Let's call this F. Maybe R. Here's R, because here's vector R. Here's vector F right here. Vector F. And it's R cross F, which means I have to take vector R and swing it into vector F, R cross F, like this. So this is the direction of my fingers, and you can see that my fingers are pointing in, my thumb, I should say, is pointing in this direction. So curled fingers, I'm showing the direction of curled fingers. I am curling R into J, and my thumb is pointing in positive K. So in the case of R cross F, this would actually be tau. So there's a lot we can say. Well, I've said a lot. tau is always perpendicular. This is good stuff. I actually was talking about E&M this morning, almost having the identical conversation. In fact, I think it was the identical conversation because, well, up to a point. You can see from this that torque is always perpendicular to F, and torque is always perpendicular to R, and torque is always perpendicular to the plane formed by R and F. So this is good stuff. This is good stuff. Anyway, that's way off on a tangent, but it's related. So back to step number 1. All right, MG, right-hand rule, or if you like this, I'm curling. Here's M. So I'm still kind of on this tangent, to be honest. So here, this would be MG. And then here's my R vector. So this is my position vector. This is the AOR. That's the AOR. So this is my position vector. I'll call it R, my R vector. And then I basically just do tail to tail, technically speaking. So these two R vectors are the same. And this R vector is technically a position vector. It's not the torque arm. It's the position vector from the AOR to the point of application of the force. And R cross F means I curl R into F. So I'm curling it like this. And you can see if this is the direction of my fingers, then my thumb is pointing out of the screen. My thumb is actually coming out of the screen. Thumb is in the plus K direction. All right, so that's a lot of right-hand rule, but good. It might not be, well, it will pay dividends. You might not see it quite yet, but you will. Maybe you're seeing it now. So this MG is positive, FN1 is positive, FN2 is negative, and F is negative. Okay. Equals I alpha. And the next thing you have to talk about is acceleration. And again, I'm just going to say alpha equals acceleration, or maybe I should do it like this. The magnitude of alpha is the same as even that's a little bit, makes me wince a little bit. Alpha equals 0, A equals 0, velocity doesn't equal, well, this is all I need right now. All right, so let me just double check the directions. MG, here's MG. MG is trying to rotate. Here's like the descriptive way. MG, you can tell what MG is trying to do. MG is trying to do this to the tire. MG is trying to rotate it in that positive direction. You can see it right there. And so this is sort of like almost a third way of analyzing the torque direction. So MG is a positive. FN1, here's FN. Oh, interesting thing about FN1. FN1 equals 0. So let's do some low-hanging fruit. 0. FN1 equals 0. Why? Well, FN1 is not 0. The force is not 0, but the torque arm is 0. So a little note here. Torque arm, and remember what torque arm is. Torque arm is the offset between the force line of action and the AORs. Here's the force line of action. All right, so I'm drawing this gray line. A line of action is just any line that contains the vector that you're looking at. This is my line of action for FN1. And notice there's no offset because my line of action literally intersects my axis of rotation. Here's my line of action, that gray line, my axis of rotation. So they're literally like this. They're doing this. They are intersecting truly in space. So there's no offset. I don't get any leverage with Fn1. That's why there's no torque produced. Fn2, you know what? Fn2, 0. 0. And why is Fn2 equal to 0? Because when tire lifts off the ground, lifts off ground surface, Fn2 goes to 0, instantly goes to 0 as soon as the wheel lifts off the ground surface. So things just got a lot easier. I have two torques. I have two torques going on. So let's go ahead. And I know the acceleration is 0. All accelerations are equal to 0 in the world of equilibrium. And I guess it should be noted that you could look at this and you could say, really, Chris, why are you saying the angular acceleration is 0? Because you could argue at the beginning, when this tire first makes contact with the curb, and it starts to actually climb up over the curb, at that point there is an angular acceleration. But I am actually trying to find the smallest amount of force. I'm trying to find out the lowest force possible to just barely cause an acceleration. In other words, I'm trying to find the minimum force that causes the acceleration to go from alpha equals 0 to alpha just being something greater than 0. So I'm right at that threshold. So that's why I'm saying, well, I'm looking for that break-even point. That's why I'm saying alpha equals 0. It's because I'm right at that cutting edge. And as this wheel does start to move up over the curb, at that break-even point, I lose contact with the ground surface, and I'm left with only these two torques: the weight, the torque produced by the weight, and the torque produced by this F force. All right, so let's finish this. Number 3, here's my new torque analysis. The torque produced by mg. So torque is force. Here's the force. There's the force times the lever arm. And the lever arm in this case, let's always go with this. It's going to be the position vector. I'll just maybe call it L1 times sine theta. Sine theta traps the perpendicularity, because remember what torque is. Torque gets produced via the product of perpendiculars, and this is going to be a plus. And then here's the torque produced by this external force. It's force times force A, I guess. No, this is force times whatever that position vector is times the sine of, I better change my angles. All right. So now before we leave here, and this equals 0. This is this is force. This is torque arm right here. I'll indicate torque arm as just R perpendicular. Over here, this is force. Over here, this is force. And this is torque arm. So that's what torque is, force times torque arm. We'll use cross products to get very, to get the product of perpendiculars between any two vectors. A lot of times it's easy. Like in this case, it's kind of easy to see this, but let's go ahead and find out what the position vector is for mg. Let me clean up this. Let me clean up all of this. So clear the decks. Here's, I don't care about Fn1. Well, we addressed Fn1. We talked about Fn2. Okay. So these are my two forces that are left standing, or these are the two forces that end up producing torque. Here's my AOR right here. That's my AOR. Here is the distance between the AOR and the point of application, the position vector. So it's always the same. It's kind of cookie cutter-ish. Ready, set, go. Right there. That's it. That's it. So this is what I'm calling L1, I guess. This is L1. L1. Okay, and to be really kind of airtight, technically speaking, when I do this cross product, or when I compute the angle, the sine theta, because I have to worry about sine theta, I should line them up tail to tail. So let me just say, okay, I'm just going to line them up, get them ready for analysis. That this is also L1, lined up tail to tail. And here's the angle between these two vectors. Ready, set, go. That's the angle. This is theta. This is theta. And I get theta. Theta is the angle between the force vector and the position vector. And the sine theta captures the perpendicularity. Let me ask you this though. Here's theta here. Let me call this just angle. Let me call this angle A. Because when I'm thinking, well, I need to find out the angle between my force vector and my position vector, this is the first thing that comes to mind. Here's my force vector, yes, and here's my position vector. So the first thing that I was thinking of is this angle A. And here's the question: how does the sine of theta compare to the sine of A? Angle A that I'm indicating there. And I'll just make up a number. Just for the sake of conversation, let me call theta. This is just for conversational purposes only. Let's just say theta is 107. If theta is 107 degrees, A has to be 73 because it has to be 180 degrees. So if theta is, and I'm just doing this as a test, if theta is 107 degrees, A must equal 73 degrees. So here's the question. Does the sine of 107 equal the sine of 73? And the calculator says sine of 107 is 0.956. Sine of 73 is also the same. So they do equal each other. So I'm going through all this nitty gritty detailed background because you have to. This is what we professionals do. So even though technically speaking, this is the angle between the position vector and the force vector, it's the same as this. So if you want to go ahead and do the tail, when I say tail to tail, I'm really meaning if you want to line these vectors up tail to tail, it's the tail of the mg vector and it's the tail of the L1 vector. You can do that, and technically that's sort of what's being referenced here, or this is equivalent. Angle A in this case is completely equivalent to angle theta. There. All right. So when I take the sine of angle A, which to be honest, that's probably going to be the angle you're going to really base your calculations on. All right, and let me just draw this a little bit smaller to take up less real estate. Here's angle A right here. That's angle A right here, angle A. So when I take the sine of angle A, I'm actually finding this dimension right here. This dimension is given as, this would be L1 sine of angle A. This is your torque arm. This is the critically important torque arm. L1 sine angle A gives me this torque arm right here. And again, you go back to torque is product of perpendiculars. And now I have the perpendiculars. This red vector that I highlighted with a green highlighter and this purple mg vector, all you got to do is multiply them together. It's mg times L1 times sine of A, which I have all of that's just sitting right here. All right, so I think I can pick up the pace a little bit now, but all this is the really nth degree detail. Done with L1. Oh, I'm not done. Number four. First of all, what's theta? Theta, and again, because I've proved it, because I went through the deep dive, I guess I can call this theta now. Theta is just the angle between these two vectors. I'm looking for the right pen. So I'm just going to call this theta. Do I know theta? No, I don't. So that's a problem. But I can play some geometry games here. I know this dimension right here is R. Here is dimension R. That's R. Radius of the wheel. That's true. Okay. I know this is H right here. So, 1 second. And I know this dimension right here, which is, things are getting hard to see, so maybe I better do a supplemental diagram. Let me erase this. Okay, this dimension you can see right there. This is R minus H. That's R minus H. So I know everything I need to know about this triangle. And this is what I'm calling L1, which is the position vector. The magnitude of L1 is just the radius. So as far as this angle is concerned, let's do trigonometry on this triangle that I'm indicating. Sine of theta. I mentioned this before. So many problems require you just to get your way to a right angle triangle. So you can use right angle trigonometry, but sine of this angle, no, I guess I want cosine. Cosine of this angle theta, referring to that little triangle that's getting kind of sloppy. Let me make it just a tad bit less sloppy. Okay, cosine of that angle is the side adjacent. Side adjacent is R minus H over the hypotenuse, which is R. Great. So I know theta. Theta is arc cos of big R minus H over R. All right. I won't calculate that now, but I know I can when I need to. So that's what theta, I know what theta is. So I know what theta is. Feeling good about theta. I know L1 is the same as R, and I know mg because I know the mass and I know gravity. So I know all of those things. And here's my dollar sign. So now let's turn attention to this second torque. I'm going to get rid of all of this stuff right here and look at F, this externally applied force. Here, once again, is my AOR. That's my AOR. So you play the same game. You basically just say, what's the position vector from the AOR, to the point of application? And then you ask yourself, what is this angle right here, which is I'm calling phi. This is phi. And just to keep myself out of physics jail, let me just once again repeat that, technically speaking, I should be lining these vectors up tail to tail like I'm doing right here. And technically speaking, I should be saying, well, this is the angle that I really need to do, that I'm dealing with. But they're the same. This angle A right here, in terms of sine, they're not the same angle, but the sine of that angle A that I just wrote down is in fact equal to sine of phi. That's because of unit circle, and my calculator said so. So anyway, just going to say, well, that's good. Just wanted to reinforce that maybe one last time. But I'm just going to go with this as my angle, that angle phi. Okay, angle phi. Angle phi, how can I figure that out? Angle phi. Well, I know that if this is angle theta, I already said this is angle theta, and I actually have a number, or I know angle theta. All right, so you can see phi equals 90 degrees minus theta. All right, so here's a rewrite of line number 3. I have mg L1, and I know what L1 is, times sine theta, minus F, which is my dollar sign, times L2, and I know what L2 is, although I'm going to draw it again, times sine of phi, and sine of phi is the same as 90 degrees minus theta. Let me just go back and look. You should get a visual on all this stuff, because I need to get a visual on the torque arm for F, the torque arm through which this external force F is creating a torque. So maybe I'm going to draw this a little bit smaller. It's still phi. All right, so this is angle phi, like that. And when I take the sine of that angle, I am showing this dimension right here. Ready, set, go. That's the dimension. This dimension right here that I just drew, this brown segment here, this is equal to L2 times sine phi. This is my torque arm. L2 sine phi, that is my torque arm as I indicated here. And you can see that L2, the magnitude of L2 is the same as the radius, because this is L2. L2 is the position vector from the AOR to the point of force application. So when I take the sine of this angle phi, this is my leverage. This is the leverage that force F has. Here's the force, the externally applied force, highlighted in green. Here's the torque arm, highlighted in yellow. There's my torque arm. And there's your product of perpendiculars. Okay, so I think you are good to go, because all of this equals 0. The left side of the equals is sum of all torques. The right side is I times alpha. Equilibrium says 0, and you are officially good to go. Let's solve for F. Mg. R minus H. I used a big R. They used a little r. Okay. One second. That's the torque, or that's the force. this force will actually just barely roll that wheel up over the curb. 13.2384. Okay. Let me get quiz 2 ready. Quiz 2 should be 27. Okay. Oops, I made a mistake. Gotta fix something. Oh, chapter 12. All right. All right. Let's move on to the next quiz. I might be able to go a little bit faster since I did some deep diving on this first problem just to cover some basics. Okay. Chapter 12, quiz 2. Apparently, it's tricep day at the old Schoolcraft gym. Which, sidebar, I don't know if any of you guys have ever been to the Schoolcraft Fitness Center. It's pretty good. And it's either free or nearly free. I think it's free if you're a student, but it's literally across the street from the Forum building, which is where our class is. So there's not much of an excuse to ever not work out unless you're into something different. But just thought I'd mention that because it's tricep day. You go up to this tricep machine and you are basically holding this handle in place. So this is statics. This is me walking up to this machine and just holding that handle perfectly stationary. And I need to apply a force so that this block, this hanging mass is suspended motionless. So I'm going to draw a thing. I'm going to do a redraw here to get maybe a bigger, easier view. This is my forearm right there. That's my forearm. So that's my body. In terms of free body diagram, this is the body. What are the forces acting on this forearm? So again, the body in terms of FBD, free body diagram, the body is the forearm. So I just drew the form. Here are my forces. I'm going to draw all the forces acting on this forearm. I have this tension force pulling here. So I guess I will call this F subscript T for tension. This is my tension force. And I'm referring to this force right here. What else? Here's my tricep force. My tricep force is also pulling up. How do I know this tricep? So this is my tricep muscle. You know what I'm going to do just to avoid confusion? Instead of F subscript T, I'm just going to use T for tension. This is T for tension, and I'm going to use this. This is my triceps force. My triceps, which is right here, my tricep, muscles can only contract. Muscles cannot extend. They can only contract. So if you flex your tricep muscle can only contract. So when your tricep muscle contracts, it's actually exerting an upward force on your forearm as indicated here. And you can see here, this is, I think, accurate. You can see there's a little ligament right there. And this ligament attaches the triceps muscle to that connection point, that insertion point onto the muscle. So that's why I'm drawing my triceps force is acting upward. Here's my humerus bone. So this is a good lesson in human anatomy and physiology. This is my humerus bone right here, right there. This is my humerus bone right there. And it's there as a support, or it's actually there as a pivot point or an axis of rotation. This humerus bone is exerting a normal force onto my triceps, and I'll show that as a force as well. Here it is, right about there. Not like that, right about there. So I'll call this F subscript H for humerus. Because here's the humerus bone. Right? I'm showing the humerus bone right here. Maybe make it more obvious. This is the humerus bone that I'm just drawing. I'm exaggerating the size and the length of it. This is the humerus bone. This is the triceps. I'm sorry, this is the forearm bone right here. This orange bone is exerting a downward normal force, because we're basically thinking this is a point-to-point connection. So it's the very point, it's the very end point of that humerus orange bone connecting with a point contact on the forearm bone. And that's why I'm saying this is the force. The humerus bone is exerting a downward normal force onto the forearm bone. So just making sure that that's making sense. I think that's making sense. But wait, there's more. There's the weight of the arm itself. We're not considering this arm to be weightless. The weight is acting on the center of mass. That's why we deal with center of mass. So the center of mass is over here somewhere. Okay, and this is mg, the weight. Those are all of my forces. I'm done with the free body diagram. And again, the rule of thumb is, do you see what a physical pivot point might be? Yeah, I do. I think this is my axis of rotation. This red dot is where the humerus bone makes contact with the forearm bone, and you get that downward oriented Newton's third law reaction, normal force as shown. So this is my AOR. So there's my AOR. There are my forces. I'm going to call this direction positive again. No reason to overturn the standard, the default convention. And now it's time to do torque. And now it's time to do the inventories. I might have to do more than just torque. Okay, is all this good to go? It is. All right, first of all, let's do our position vectors. And the position vectors are required to figure out the torque arms. So here we go with the position vectors. For FT, and let's remember what a position vector is. It's from the AOR to the force point of application. So I'm going to call this L1 for no reason, for lack of any good reason. That's the position vector between the AOR and FT. Here's the position vector between the AOR and MG. Let's just call that L2. Last but not least, the position vector from the AOR to the tension force. And I think I will use a different color because I'm going to be partially overlapping. And I don't mind overlapping, but I don't want to block out completely L2. So I'll move this just a hair. Okay, and I'll call this L3. That looks good, I suppose. All right, so let's do the torque analysis. What are the sum of all torques? Number one, the sum of all torques equals, and just don't think now, remain in a state of nearly unconsciousness and just tally up. There could be a torque due to that triceps force. There could be a torque due to the humerus force, which is that Newton's third law reaction normal force as indicated, a torque due to mg, and a torque due to tension. And what does it equal? I alpha. Just like in the good old days, we had F equals ma. Now I have tau equals I alpha, and it equals 0 because of statics. Nothing's moving. All right, so now let's worry about the sign. So I'm going to use my right-hand rule number 2, and I can see using right-hand rule number 2, this is going to get a negative. Right-hand rule says that this is going to be 0. There is no torque arm. This is going to be negative. This is going to be positive. So we should talk about this unless it's clear. If it's not clear why I'm saying that's negative and that's negative and that's positive, definitely speak up and why this is equal to 0. But this is what we should talk about. Absolutely. Because if you're clear on this, if you're clear on all of these little nagging and there's not an infinite number of them, but if you're clear on just a small set of these naggy little details, then that's going to make a big difference. Here's the torques. I have minus the torque due to this FT force times the lever arm times the sine of, I guess I'll call it theta 1. Where, again, this is the torque arm right here. I am showing you the torque arm, R perpendicular, again, is a shorthand notation for the torque arm. Visually, what are we talking about here? Here's theta 1, which is the angle between that green vector and that purple vector. It's the angle between the force and its position vector. FT. That's not theta 1. Yeah, that's not theta 1. All right, here, this is theta 1. All right. FT, there's my position vector. There's the angle between my force and my position vector. And when I do that, you guys, when I take the sine, when I do L1 sine theta, I am actually getting a really good picture of what my torque arm is right here. This black line, this is in fact L1 sine theta 1. That's my torque arm. You can see how it's perpendicular to the force. This is my torque arm. Okay, so it's good to see that. It's good to see that. But now that we've seen it, I'm just going to put it away just to clear the clutter because things can get hard to read otherwise. Okay, so now let's move on to the torque produced by the weight force. Ready, set, go. That would be negative force. There's the force times the position vector, which would be L2, times sine of theta 2. And where's theta 2? Well, here's theta 2. Ready, set, go. Okay. Theta 2 is the angle between the position vector. When I move my AOR, let me move my AOR back. Okay. Theta 2 is the angle between this green vector that's being partially blocked by that orange vector. But there's L2, there's mg, and there's the angle between them. Okay, and you can see from here, you can see theta 1 is going to equal theta 2. All right, last but not least, this should have been the torque due to tension. This is torque due to tension, T. Okay, so making that update plus the force, which is this tension force, times its position vector, L3, times the sine of the angle between those two vectors. Here's L3, so it would be, this is theta 3, right here. Theta 3. That's theta 3. And you know what? I can't help but notice that if I just added these grid lines right here, I'll leave it. But all right, that's it. Equals 0. Equals 0. So what can we find from this? Let's just do a little sanity check here. Do I know, what do I know here? FT, this is my dollar sign. L1, do I know L1? Let's do a little L1. L1, I'm showing L1 here. L1 is given as D2. So I do know L1. L1 is D2. For me, it's 0.021 meters. Do I know L2? L2 is the distance from the AOR to MG, which according to this, that's D1. And last but not least, do I know L3, which is that orange vector? That orange vector is from the AOR, which is this COM point. There's my AOR, all the way up to where that tension force is applied. And that is called D3. Okay. So I'm just going to do a double check. L1 is the distance from the tricep muscle and my AOR. And this is my AOR. This is my AOR. Okay. So yes, L1 is the same as D2. L2 is the distance from the AOR to MG, from the AOR to the COM, and that is D1. L3 is the distance from the AOR, this orange vector, to the point of application of the tension force, and that's D3. All right, they give you this as theta. They're saying this is theta. Okay. So they are giving me that as theta. So for me, theta 1 equals 90 degrees minus theta. Theta 2 equals theta 1 because they're alternate angles. Here's theta 1, and then here's this bisector transverse. There's my transverse, and then here's theta 2. So theta 2 is equal to theta 1. What about theta 3? Maybe I'll do a couple of guidelines here. Let's see if I did this. Grid line, like just some useful reference lines, just so I can maybe see some things. So I can see the force through the trees. I'm always doing stuff like this just to give myself, some perspective. Well, okay. Can I find theta 3? Yeah, I can. This is theta 2, which equals theta 1. So this is theta 2. So theta 3 is going to be equaling 180 minus theta 2. All right, so at this point, I have all of my position vectors. I have all of my angles. Everything is known here except for this dollar sign. Go ahead, let's find that dollar sign. F sub t equals, and then let's do the work on it. MG. Oh, you know what? I got to add a little number 3. I know everything except for that tension force, although I think I know it's tension force. All right, I'm just going to include a step number 3. This tension force, this equals the weight of block. Tension force is the weight of the block, so I can basically say, I can substitute the tension force for the weight of the block, mass of the block times G. I can say that because things are motionless. If things were moving, then I ran, this was sort of the misstatement I made before. I actually can say right now that the tension force is the weight of that stationary block if that block remains stationary. I mean, we could do a whole Y force inventory, but at this point, we know everything. We know everything because that's M block times G. Okay. All right. D3. $22.68. I know you guys still might be calculating. Let me just lay out a game plan for part B and then unleash you guys. For part B, we're saying what's the humerus? So what's FH? What is the force acting on the forearm from the humerus? That is part B. And for that, I'm going to do a Y force inventory. This saying F subscript H is the $sign. So I'm going to do sum of all Y forces. And I've got FT, which I now know, going up. FH is going down. MG is downward oriented. In fact, I better word, well, MG is downward oriented and tension is upward oriented. This is mass times A sub Y. A sub Y equals 0 because statics. And I guess that's it. That's all you need to do. Let me do a sanity check here. I know F sub T because I just figured it out. This is my $sign. MG, this is the mass of the forearm. It's the mass of the forearm times G. This is, yeah, I already noted that this tension is just brought to you by the mass of the block times G equals 0. Okay. F sub H equals FT minus mass of the forearm Okay. Got part A, got part B. Right now, you should see chapter 12, quiz 3. It ideally looks like this. More equilibrium, more statics, more static analysis. And again, most of you will take an entire class on this stuff. Obviously it will be more advanced, but most of you will take an intro to engineering. Most of you will take engineering statics, engineering dynamics, engineering materials and engineering, I guess that's it. Is that it? Oh, circuits, and then a circuits class. So this is sort of the group of pre-core major, pre-major engineering prereqs. They're all engineering classes, but they're sort of horizontal. They kind of span all fields of engineering. So we are, again, focusing on statics. Materials is part of chapter 12, but I'm just sort of sidestepping it because the chapter 12 treatment of materials is very superficial. But I did include it in your green sheets as reference, as like very basic reference. Okay, so here we have a situation, this non-uniform bar, and that catches my eye. That should catch your eye right away. This non-uniform bar. Non-uniform means one thing. The center of mass is not the same as the center of the geometry. Because if I'm looking at this bar, I'm thinking, well, this blue dot is the center of geometry, about there. And that's not where the center of mass is. The center of mass is not located at that blue dot because it's non-uniform. So this is what you as a materials engineer would design based on design specs, is an object that has varying density. And I think we need to find X. So given this situation, what is the value of X? What does X need to be for this bar to be perfectly at rest horizontally, in the horizontal position? I want to get a better picture of that. Let me go to the textbook and just do a snip. This might be easier to view. Okay, so free body diagram. Free body diagram time. I have here's my tension over here. Here's tension over here. Here's my weight force right there. Okay, so this is mg. This is, I'll call this TL. TL is the left side tension. TR is the right side tension. Those are all my forces. I can't think of any more forces. I don't think I'm missing any more forces. Where's the AOR? And at this point, I don't know. You know, there's no physical, and there's no intuition based on the physical situation. There's no physical system based intuition I have. So I don't know. So you know what? Because I have no idea, then I'm just going to go out on a limb and say it's right here. Here's my AOR. And here's the point. Well, maybe should that be my AOR, the far left side or the far right side, or here, or go ahead, put it here. And the answer is, I don't know. So I'm just going to go again, arbitrarily, just drive a stake in the ground and say, that's my AOR right there. And I'll deal with it. I'll deal with it. Maybe there would have been an easier selection, but I don't know. At this point, I don't have any special insight. The only thing I know is the torque about all AORs. Any AOR I can conjure up, the torque has to be 0. So I'm just scratching my head. Is there any reason? But I can't see any reason not to use this. Maybe I will shortly, but let's do torque analysis. Sum of all torques. The sum of all torques, and then let's play the game. I have the torque due to that left side tension the torque due to the right side tension, the torque due to mg. All those torques have to equal 0. There's no angular acceleration. There's my AOR. Here's my standard default rotational coordinate system. So having said that, I can see that TL produces a negative, TR produces a positive, MG produces nothing because there is no torque arm, low-hanging fruit. Okay, so I can say the following. Number 2. Negative of this left side tension force times the torque arm, or I'm sorry, times the position vector. Here's the position vector right here. This position, I'll draw it. It looks like this right here. There's TL. There's the position vector from the AOR to the point of application. That's it right there. And that's equal to X. So there's my $ minus TL times X. Got it. Plus my right side tension, TR, times its, oh, and I forgot the sine theta. Back up. X is the position vector. X sine theta, I guess I'll do sine theta L, is the torque arm. So let me just stress this. Just take the opportunity to say that X times sine theta L, that's the torque arm. Where's theta L? It's right here. It's this distance. It's this angle. It's the angle between those vectors right here. This is theta L. Which would be, if you wanted to, if I was going to call this angle A, it would be the same, because as mentioned, sine of angle A is going to be the same as the sine of theta L. All right. The right side torque is the force. Here's the force. All right. So plus the force, T subscript R, times the position vector, which is right here, from the AOR to the point of application. There it is. And that position vector is L minus X. TR L minus X times the sine of theta right. And all that equals 0. Where's theta right? It's right here. It's this angle. This is theta right. This is the angle between the right side force and the position vector, or alternatively, I could call this angle B. Sine of angle B equals sine of, and I'm just doing that just in case it's easier to get B compared to theta R. But they're both for sure knowable. All right, here's my $. So I see the presence of my $sign is right here. There's X, and here's X. But there's a problem. I don't know TL, I don't know TR. But I do know. All right. So I need some more equations. I have too many unknowns. So there's the result of my torque inventory. Minus TL X sine theta L. All right. So let's do an X force inventory, because I need to just crank out some more equations. And then I'll do the whole simultaneous equation endeavor. All right, so here is sum of all the X forces. All right, so here's an X force right here. I have to decompose it. Here's an X force. And here's an X force right here. And while I'm here, I guess I'll draw the Y forces. Here's a Y force. And here's the Y force over here. Labeled. This is TLX. This is TRX. This is TLY. This is TRY. Over here, TRY. Okay. So as far as sum of all the X forces, I have minus TLX plus TRX equals MAX equals 0, because A sub X equals 0 because of statics. Okay. So before I move on, I guess I can process this. So you know what this means? This means TLX equals TRX. And you can see that. You can just look at it. You can say, hey, whatever this force is, it has to be equal to this force. Because if things are in equilibrium, that has to be. But we've done the formality of it. All right, here's TLX. TLX is TL cos theta, right? No, sine theta. Got it. Equals TRX. TRX is TR sine phi. Let me just check this. Let me just do my triangle thing. Over here, for this triangle right here, I'm saying, well, and this is theta. If sine theta is opposite over hypotenuse, that's how I'm getting TLX equals TL sine theta. Okay, over here, I'm saying, and this is phi, I'm saying sine of angle phi equals opposite TRX over TR, and that's how I'm getting TRX equals TR sine phi. Good to go. Can I, so I am looking at the fruits of my labor. This is the result of my torque inventory. Okay. This is the result of my X force inventory. There's only, I have three unknowns. I have TL, TR, and X. So let's just do one more inventory, and then I think we'll be good to go. We should be. I'm going to do a Y force inventory. Sum of all the Y forces better equal to 0, and I have the following. I have TLY is going up, plus TRY is pulling up, minus MG, which is pulling down, equals M A sub Y. A sub Y equals 0 because of statics. So I have number 6, TLY would be TL cos theta plus TRY, which would be TR cos phi equals mg. That is it. I have my third inventory. I have 3 equations with 3 unknowns. So let's spend a chunk of time solving. normally I say, you know what, we don't need to spend all this time doing algebra, but I think it's good. I think one of the reasons why you guys do kind of well is you're good at the algebra, and I don't want to mess with that. Even though I kind of cringe a little bit because this is a physics class, not an algebra class. However, it is what it is. The reality is sometimes the algebra is the toughest part. So I'll noodle off on my own. You are welcome. In fact, you are encouraged to ignore me and do your own thing, because you're not going to be able to glance at my work during the exam and follow what I'm doing. But I'll work sort of silently and independently. And if you get too stuck, you can take a peek, but try to ignore what I'm doing. All right. So, typo alert. I got to erase this. Attention shoppers. This is TR cos phi. Okay. 3.3. Sine of phi. Right for that. $257. Let's do one more quiz before a break. Chapter 12 quiz 4. Chapter 12 quiz 4 is 33. Okay, chapter 12, quiz 4. Statics. What a shocker. All right. Let's start. We have a vertical uniform beam. That's a keyword, uniform. This term uniform means that the center of mass is the same as the center of geometry. Uniform means that. So this little dot right here that I'm drawing, that looks like if that's the center of the geometry, that's also the center of mass, right at that halfway point. Let me get a better picture. This is problem 33, something that's easier to look at. $33 is right there. Okay. All right. Okay. So a vertical uniform beam is hinged, and this is a very key term. A hinge is a special element in the world of engineering in general. You saw the hinge element in interactive physics. So here's the hinge. This hinge, and this hinge is basically, this hinge does two things. This hinge actually provides a horizontal force to prevent this beam from moving horizontally. I don't know the direction of the hinge force. I'm just going to arbitrarily say, well, without knowing anything, I'm just going to call this the hinge's horizontal force. So maybe just F subscript H. Again, I don't know if it's pointing to the left or pointing to the right, but that's my guess. So the hinge will prevent horizontal motion, and the hinge prevents vertical motion. Both of these are normal forces. So here is the hinge's vertical force. This is the vertical force acting on the beam due to the hinge. Okay. As long as I'm doing free body diagrams, this is the tension force. I suppose that's good. T for tension. There's a weight force. There's a weight force, and if it's uniform, the weight force is just acting straight down from the center of mass, like that. And this is mg. And I think those are all of my forces. Tension, oh, and F subscript A. So let me just, tension due to the cable, the hinge force, which is a normal force, the horizontal force from the hinge acting on the beam to prevent horizontal motion, the vertical force coming from the hinge acting on the vertical beam to prevent vertical motion, and the downward pull of gravity. And then there's an external force, F subscript A. Maybe it's a gust of wind, maybe it's a steady wind, or maybe you're just leaning on this post, or something is providing that external force, F subscript A. I think those are all of my forces. And now we have to read the problem. This external force is applied at the beam at distance y. Right, so it's applied at a distance y. And apparently this is a movable force. According to the graph, this force can be applied anywhere, but it is the sort of a horizontal force, which I'm assuming it's not a variable force. It's just a given horizontal force that I can apply at anywhere along that vertical beam. The beam remains vertical because of the cable attached at the upper end with the angle theta with respect to the horizontal. And then I have all these graphs. So let's try to make heads and tails of this graph. I have a graph of tension versus Y over L. And it says here, figure B gives the tension in the cable as a function of the position of the applied force. This is the applied force, F subscript A, given as a fraction of Y over L of the beam length. All right, so you know what? Let's just be careful and interpret this. All right, if this F sub A, if F sub A, maybe if F sub A, if that external force is applied at Y equals L, that means Y over L equals 1. And I'm looking at this point. All right, so if I apply F sub A right here, for example, if I applied F sub A at the very end of this beam, it would look like that. like, well, keep things. All right. So if I move this F sub A all the way to the end of the beam, that means Y equals L, Y over L equals 1, and tension equals T sub S because of this. This is corresponding to Y over L equals 1, and that's T sub S. So if F sub A is applied at Y equals L, that means Y over L equals 1, and T equals TS, which for me, TS is 600 newtons. Okay. So that's good to know, I suppose. What about if, and I'm just, again, spending a lot of time trying to digest all this graph stuff. If F sub A is applied at Y equals 0, that means Y over L equals 0, which means now I'm looking at this point right here. And that means T equals 0. Okay, fine, I guess. Can I get anything out of this? Not yet, I don't think, other than just graphical interpretation. So what if this is the graph in B? Let's talk about the graph in part C and have the same conversation. Okay, this is saying figure C gives the magnitude of the horizontal FH. They used a little h, I used a big H. So this is showing what's going on with the hinge. This is the hinge. Maybe I'll change this to be consistent, not F big H, but F little h. So graph C, the graph in C is showing what happens with that force as a function of that F sub A, the horizontal force. This is F sub A. So in both cases, I guess I'm moving F sub A all around, and let's see when if F sub A is applied at Y equals L, that means Y over L equals 1 over here. And if I'm applying this force at Y over L equals 1, that means my FH is 0. Okay, if F sub A is applied at Y equals 0, then Y over L equals 0, which I'm right here now. And that means F sub H. Oh, that's going to be useful. F sub H equals 1, 2, 3, 4, 5. Except this isn't my graph here. Actually, I got to be careful. 600 was right, but here, for me, I needed to change these numbers. My numbers are, this was 200, I guess. This was 200. And then this would have been 100. So this is 250. F sub H equals 250 newtons. Let me go through and check that. If I apply this external force at Y equals 0, meaning down here, I'm applying this force, not up there, but down here. Wait for it. Please stand by. Please stand by as I restart notes. Let's see. All right. If I apply this external force down at Y equals 0, that means Y over L equals 0, which means I'm looking at this point. And when that's the situation, when I'm applying this force on the hinge, my hinge has a reaction of 250 newtons, which is right here. because that's for me, that's 200. That's what. So you know what? This is an aha moment. So I can say right here, aha, F sub A equals 250 newtons. So I got that right now. And I think that's the answer to part B. Part B says, what is F sub A? And I just found F sub A just doing this, you know, my inner dialogue interpretation of these graphs. So because F sub A is constant, and that's sort of the thing I was kind of not remembering. F sub A is a constant force. It's a constant force, but you can apply it at any point along the beam. It's a constant force. And if it equals 250, as soon as I get a number on it, and right here, I basically got a number on it. I said, well, the hinge force equals 250, and that actually has to be the same as F sub A when F sub A is applied at y equals 0. When F sub A is applied at y equals 0, then my hinge force, oh, and you know the other things I can update. So this is saying, this graph is saying, well, I have my answer. I'm going to update F sub H because I know what's going on physically. F sub A is for sure always pointing to the right. There's no equivocation about that. This is F subscript A is always pointing to the right. And I just got done. I just kind of showed, maybe I should sort of number this. Maybe 1, 2, 3, 4, 5, 6, 7. I just from steps 6. In step 6, I showed F sub H equals 250. And I know for sure it has to be going to the left like this, because F sub A is given as going to the right. So that this is the only alternative I have, or this is the only choice I have. This is F subscript H. Okay. It's going to the left. And when F sub A is applied at y equals 0, my graph says this is 250 newtons. And that has to equal F sub A. And we could do a X force inventory. So number 8, I could say, let's do an X force inventory when Y over L, or at y equals 0. Let's do a X force inventory at y equals 0. Which you see there in the picture. Ready, set, go. I have negative F sub H equals F sub A. Actually, maybe a little more formal. Plus F sub A equals MAX equals 0 because of statics. So that's how I'm saying F sub H equals F sub A equals 250 newtons from graph. There. That's the answer to part B. Part A wants theta. What's angle theta? This could be a job, I think. I guess my first instinct is to go with torque analysis. I guess. Yeah. Maybe, let's see. What about T sub? Do I need torque analysis? I guess so. Maybe I could do another inventory, but let's do a torque inventory, which says the sum of all torques. And then I got to establish an AOR. So it's back to business as usual. There's my AOR. That's my AOR because that seems to be the natural choice. That's where my physical AOR is. AOR. Okay, so that does make a lot of forces drop off. A lot of torques are just going to be equal to 0. All right, so I have now. Where should I do this torque analysis? Torque analysis. I should say I need to specify. I should do my torque analysis at y equals something. I guess let's see. Let's do the torque analysis at y equals L. Torque analysis at y equals L, just so I can bite into some actual numbers to work with. Torque analysis at y equals L. It's interesting. Okay. Here's what I get. I get sum of all torques equals 0. Sum of all torques is the torque due to all of those forces, that tension, the hinge's vertical force that it's applying to the beam, the hinge's horizontal force, which it's applying to the beam, the weight of the beam itself, and the torque due to that externally applied force, F subscript A, which I have a number on that. All right, and this equals, all of that equals 0. And I think I have everything here. Okay, so let's do signs, the torque signs, the signs of the torque. Ready? These are all equal to 0. This is equal to 0 because there's no torque arm. This is equal to 0 because there's no torque arm. Same here. And I'm left with 2 torques. 2 torques are left standing. Number 9, number 10. Oh, and then my signs, let's see. What's the direction of that tension force that's positive? Using the right-hand rule, you can see that this tension force is trying to swing the beam this way. It's trying to do that to the beam. That's what we're calling positive. Although I should specify that we're calling that positive because of our rotation direction. Anything counterclockwise is positive. That's why that gets a positive sign. This is why this gets a negative sign. Okay, so step 10. Ready for the torques, I have that tension force times its torque arm, L1, times the sine of the angle between those two, minus that FA force, which is 250 newtons, times its torque arm, times the sine of the angle between those two equals 0. So I should be able to get the tension force here somewhere. No, I should be able to get theta here somewhere. So let's go ahead and figure this out. All right, let's clear the decks. That's just too messy. All right, so here's my tension force. That's my tension force. This is the position force from the AOR to the point of application. And this is what I'm calling theta 1. This is theta 1. That's theta 1. This is T for tension. This is my position vector right here, which is the same as L because I'm doing all of this at L. This is, as shown, L. So let's update all of that. Number 11 comes from number 10. T times L times, let's talk about theta 1 here. I can see that theta 1 equals 90 degrees minus theta. Theta 1 equals 90 degrees minus theta. Sine of 90 degrees minus theta minus FA, which is 250. What's L2? I'm applying this at y equals L. So this is also L times sine of theta 2. All right, so for FA, clearing the decks a bit, I'm saying let's look at life when I apply FA at y equals L. So there's FA. So we're temporarily ignoring this. Here's FA applied at y equals L. And you can see what's this angle between these two? It is 90 degrees. So theta 2 equals 90 degrees. And that position vector from this AOR to the point of application equals L. All right, so as stated. So sine of theta 2 is sine of 90. I guess is that good? Sine of 90 equals 0. The L's cancel. L cancels, L cancels. T at y equals L. For me, T equals 600. At y equals L, which means y over L equals 1. When I'm applying my force out at that outer point on the beam, I have 600 newtons for tension. So I have 600 newtons for tension times the sine of 90 minus theta, there's my dollar sign, equals FA, which is 250, equals 250. Okay. So number 13, I can get sine of 90 minus theta equals 250 over 600. 250 divided by 600, which means the following. 90 minus theta equals the inverse sine of 250 over 600, which means theta equals 90 degrees minus inverse sine of 250 over 600. 90 minus inverse sine of 250 divided by 600. 65 and some change. Okay, and that's the answer to part A. Let me do this. Screen. This is why, this is sort of one of the goals of doing force analysis. Here I have a piston rod and I'm doing force analysis. And when I figure out what the forces are acting on this part, I can basically do something called finite element analysis. And everything that's in red, it's color coded. So blue, I'm assuming blue means low force, red means high force. So one of the things that you would do with this information is you've done your force analysis, statics, your force analysis, and you're saying, well, okay, I have to make sure when I design this part that I make it I make it strong in the red areas, that the tensile strength or the compression strength of this steel or whatever the material can withstand these forces, otherwise it breaks. And then sort of by the same token, if you wanted to, you could say, well, I don't have to have as much I have to have lower tensile properties or compression properties in the blue area. And for this part, it probably doesn't make sense, but for more expensive parts, you might want to just have sort of a hybrid material where you have strong material where the red is and weaker material where the blue is, depending on a lot of other factors, but just wanted to show you the finite element mesh and the input. So you design this part in CAD, like CATIA or whatever CAD system you might know, or whatever CAD system you might learn. And then you say, okay, I have my geometry. Now I'm going to apply the forces thanks to force analysis. And then this is going to tell me where I have the greatest stresses and strains. And stress and strain, those two terms are actually in chapter 12. So let's do one more quiz. All right. A plank is leaned up against an edge like that. It's staying in equilibrium for theta, for any value of theta 70 degrees or more, meaning the more vertical it gets, if it gets more vertical, it remains in equilibrium. If it gets more vertical than 70 degrees, it will stay in equilibrium. If it gets less vertical than 70 degrees, it slips. And now we have coefficient of static friction. All right, so let's just do the ground. I'm just redrawing it just for a larger view. All right, there's the ground. Here's, well, okay, here's the table. It's like leaning up against the table. Okay, and then here's like a plank. It's a plank. Here is the plank. Okay, leaning up against a plank. All right, so let's do some free body diagramming. Here's the normal force. This is a normal force. This is the force on the roller. It's a roller, so frictionless roller. So if this is a roller, the normal force would look like this. I'm trying for a different color. Okay, so this is technically a normal force, F subscript N. I'm going to call it 1 because we might have another. I think we have another normal force down here on the floor. But let's just make sure this is 90 degrees because it's just a roller. So this is 90 degrees. That's one of the forces. We know that it has a weight. So this is not massless. So we're kind of done with the era of being massless. So here's another force. It's the weight force. And it's uniform. So this uniform means the center of mass is the same as the center of geometry. So I don't know exactly where this center of mass is with respect to that roller, but I'm just going to guess right here. And I'll have to find it out for sure. But that's the center of mass right there, which means there's a weight force acting on that center of mass going vertically downward. Okay. But wait, there's more. There's more forces. This is mg. There's static friction. Static friction is what's preventing this from sliding. Because if there was no static friction, it would slide immediately for any theta greater than or less than 90. Less than 90. Okay. Any angle, if there was no static friction between the plank and the floor, unless it's perfectly vertical, it will slide. So static friction is doing this. This is static friction right here. The green bar, or yeah, my plank, it's too bad I didn't make that red, but my plank here is tending to slide to the right, but this is static friction, keeping things, which let me, I guess, go to blue. Okay. Static friction. And the last force I have is another normal force from the floor acting on the plank, on this end of the plank. Okay, Fn2. That's it. Once again, being hyper diligent with my free body diagram. So now the question is, let's do the torque analysis. What should I call my AOR? What should I call my AOR? Again, it's tough. It's tough. I'm going to do this. I'm going to call this my AOR. I'm not seeing a physically obvious axis of rotation. Obviously, I'm thinking, well, is this my AOR, or maybe is this my AOR? So I'm not seeing nothing's popping out as obvious. So I'm going to call this my AOR right there. Okay. So let's do the analysis. There's one advantage in calling that the AOR. If I call this the AOR, then right away I take out two of these forces when I do my torque analysis. So that is kind of rattling around in the back of my head. And you'll see that right here coming up. Now let's do the sum of all torques. I have the torque due to Fn2. Maybe there's a torque there. Maybe there's a torque due to F sub S. Maybe there's a torque due to mg. And maybe there's a torque due to Fn1. They got to equal 0 if we're in static equilibrium. And this is what I'm saying. This is the advantage in choosing the AOR the way I did, is because right away you can see no torque, no torque. mg is producing a negative torque. Plus alpha. So this can have a negative sign. Fn1 is producing a positive torque. Okay. So as far as torque analysis is concerned, I have the torque produced by mg has got to be equal to the torque produced by Fn1. Right? Okay, so that means mg is the force, L1 is the position vector, sine of A is the angle between them. So mg is the force, here's the position vector. Right here, okay. That purple vector. Okay, and here's the angle between them. A, and that's knowable because this is theta and this is 90 degrees. All right, so this is my force, this is my torque arm. I'm calling this L1. All right, what about the torque due to Fn1? That equals the Fn1 force times its torque arm, which is, I don't know what that is. I'm going to have to figure it out. So just call it L2 times sine of B. All right, so here's, better get creative with color. Here's my position vector for Fn1. It's that orange vector. And at least I know what B is. B is 90. Okay, and this is L2. Okay, L2. And B is equal to 90. B is talking about the angle between those. This is angle B. All right, so number 3. This becomes number 3. MG L1, MG. Okay, all right, here you go. MG times L over 2 times sine of 90 minus theta. That's good. Equals Fn1 times, let's do a little sidebar here. Fn1 is right here. So I need to figure out what is this dimension here. It's H. So here's my triangle. There, there, and there. Okay. So let me make that a little more readable. And I'll come back and talk about all this again, just to check myself. All right, so I am talking about Fn1. Here's Fn1 acting over here in this diagram. This is Fn1. So now I need to ask myself, that's not, I don't think that's L over 2. At least I can't say that's L over 2. Maybe it works out that way, but this is why I'm setting things up like this. Okay, so here's my triangle. That's my position vector. This is H. And then that's this side of the triangle. Okay, so if I do a little trig there, I can say sine of theta equals H all over what I'm calling that L2, because this is L2. This is L2, which is the position vector from that AOR to the point of application, in this case of Fn1. Okay, so sine of theta equals side opposite over hypotenuse. All right, so L2 equals H over sine theta. Okay, so let's go over here. L2 is H over sine theta. And let's double check this. This was a result of my torque inventory. So before we punch in the final numbers, this was my mg force. Mg was acting on the center of mass. And the center of mass for a uniform plank is just going to be L over 2 at L over 2 because it's uniform. All right, so I'm feeling good about this position vector. What's the angle? What is this angle A? It's going to be sine of angle A gives me the torque arm, and be sine of angle A is the same as 90 minus theta. I'm feeling good about that as the torque due to my weight force. Fn1, there's my force, and my torque arm is H over sine theta, because over here, sine of theta equaled H all over the hypotenuse. Okay. There it is. The only problem here, I got to solve for mu sub s. Find the coefficient of static friction. Okay. So let's keep going.
Are you missing the sine B?
Sine B was 90.
Oh, okay. Thank you.
So let me do that. Sine of 90, because you're right. Okay. Very helpful. All right. So I need to find out mu, where the heck does mu sub s live? All right. So right now, this might have been a waste of time. I mean, it wasn't, but at this point, I just did this torque inventory just as sort of a standard starting point, just force of habit, because I don't see mu sub s anywhere. So now if I do a X force inventory, an X force inventory says, well, I've got F sub s, and there's my dollar sign, F sub s minus this X component here. That's Fn1x. This is Fn1y. Getting quite the trig workout in geometry. So this is Fn1x, Fn1x. This is Fn1y. Okay, so back to my X force inventory, plus F sub S is going to the right, minus Fn1x is leftward oriented. Equals 0. So let's just hammer on this for a few more steps. Well, it technically equals MAX and A sub X equals 0 because of statics. Okay, so I have mu subscript S times FN1, FN2 minus Fn1x. All right, so we got to play angles. Let's see. If this is theta here, then this is theta here. If that's theta, and for me, theta is 70. So that's 70. That must be 70. This has to be 20 is one way of doing it. A way of doing it. All right, so Fnx is going to be, Fn1x is Fn1 cos theta. Fn1 cos theta. And these two are equal to each other. Okay. Let me double check all of this again, since I'm trying to wrap up. I'm trying to make it a little brief since it's getting late. It's been a long night. This is my X force inventory. I'm saying my static friction force, which is the only thing between me and disaster. Static friction is the only thing preventing this plank from slipping. It's going to the right. So yes, plus F sub S. Fn1x is right up here. This is the leftward facing force. This is minus X. And let me double check myself with my angle game. I'm just saying, okay, if this is theta, then that's theta. And in my case, theta equals 70. And I know I can see that, this is 90 degrees. And then that means this is 90 degrees. So if this is 90 degrees, because this is a normal force. So if that's 90 degrees and this is, so that's my thought process for getting this 20-degree angle in that triangle. And you can see that cosine of 20 degrees equals Fn1x over the hypotenuse Fn1. So that's why down here, this became Fn1 cosine theta. Okay. Okay, so there's my dollar sign. The only problem is I need to do I still have too many unknowns. I'm going to do one more Y force inventory, and I think I'm going to be good to go. But let's see, Y force inventory. Y force inventory says what's going up. Fn2 is going up. What else is going up? Anything? Yeah, Fn1y plus Fn1 sine theta. And let's just do a little double check. Sine theta for this triangle equals side opposite, which is Fn1y, all over the hypotenuse. So that's why I'm saying Fn. I better be careful. I am calling these 20 degrees. So that actually would have been a mistake. So Fn1 sine of 20 degrees. So let's put the actual number in there. And this was Fn1, and this was also sine of 20 degrees or cosine of 20 degrees. Okay, so almost a mistake there. All right, so my Y force inventory, I have these two forces going up, Fn2 and Fn1y. Yes. And then I have mg coming down, minus mg equals 0. All right, so from all of this, I am thinking I can get my mu sub s. So let's just tally things up here. This is the result of my torque inventory. This is the result of my X force inventory. This is the result of my Y force inventory. Okay, and I just want to check that before. Okay. Mu sub S Fn2, F sub S equals Fn1. Okay.